Solve 2x plus 3 equals 4x minus 5. So we've got this familiar word here, solve. And we know that solve means work out the number that the unknown letter, x in this case, is code for. So our very final answer for this question should be x equals a particular number. Now we've already seen one way of solving, and the way that we've seen of solving things is by setting up a function machine. And we might be tempted to do the same here, because solve to us, as far as we are aware, means set up a function machine. Well, the first problem we've got to start with, when we set up a function machine, we have to start with this unknown letter x and write down what we are doing with it. Problem is, are we going to be looking at this x here, that's got the 2x attached to it and then the plus 3, or are we going to be looking at this x here? Well, actually, okay, maybe it doesn't really matter. Let's say we start with the one on the left, because that's perhaps more familiar to us. So let's start with this x here. We're going to set up our function machine. Well, the very first thing that happens to it is it becomes a 2x, so we times it by 2. And then we need to add 3 to it. And when we go through that process to become a 2x plus 3, that spits an output out the other end of the machine, the function machine, and the output is 4x minus 5. 4 lots of this number x minus 5. So already that seems a little bit weird, because we are used to seeing a single number coming out the end of it. Whereas here we've got another bit of algebra. But okay, fair enough, maybe it doesn't actually matter, maybe it will still all work out. So in theory then we can reverse the function machine. We can put the 4x take 5 back in. Instead of adding 3 we'd be taking 3 away, and instead of timesing by 2 we'd be dividing by 2, doing the opposite as we reverse the machine. 4x minus 5 goes in and then we take away 3, so that will be 4x take 5 and then take away another 3. Well, the take 5 take 3 would combine to become a 4x take away 8. Interesting, okay. And then we're going to divide that by 2. So then dividing that by 2 we'd get, well, the 4x divided by 2 will be 2x, and the minus 8, the take away 8, dividing that by 2 would give us a take away 4, and we're coming out with 2x take away 4. And then our final answer would be x equals 2x take 4, and that actually doesn't look any better. We've not got any closer to an answer. Okay, fair enough. Maybe we were wrong in picking the x on the left-hand side of that equals to start with. Maybe we should have done the same thing with the one on the right-hand side. Let's have a look at this again with the one on the right-hand side then. So let's restart with the x as given to us on the right-hand side of this equals sign. So we start with the x. We're going to build our function machine for that side of the equals sign. First thing that happens to the x is it becomes a 4x, so we times it by 4. After that, we have to take 5 away from it to give it the 4x minus 5. And that spits out 2x plus 3 as an output. Once again, a piece of algebra rather than a number. We could still reverse it all the same though, and fingers crossed this goes better than it did last time. The 2x plus 3 goes back in, and we are going to add 5 to it first of all, and then we are going to divide it by 4. 2x plus 3 add 5, well that would be 2x plus 3 plus the 5, and the 3 and the 5, the plus 3 and the plus 5 will combine to give us a plus 8. We are then going to divide that by 4. Well, we could do that again. We could do 2x divided by 4. Well, that would be a half of x. 2 divided by 4 would be 0.5, or a half if you prefer. And the 8 divided by 4, that would be a plus 2. And then we're saying that x equals a half of x plus 2. And that doesn't just not seem better, that actually seems worse, because suddenly we've got a fraction or a decimal in there. And surely that leaves us with a little bit of a problem. So the question then is, what can we do instead? Well, actually, we like using those function machines. Those function machines work for us. They are easy to use, easy to set up, and they are easy to solve questions with. So really, if we could turn this into a problem that we could solve with a function machine, that would be ideal. This currently is not solvable using a function machine. But if we could muck about with it in some way, if we could fiddle a question somehow to turn it into something that we can solve with a function machine, that would be really good, because then we'd just be able to use a function machine no problem. So our second step on solving these questions is going to be use the function machine. But we're not there yet. Our first step is going to be to change questions like this in some way to get them into something that we can solve with a function machine. So how are we going to do that? Well, the very first thing we're going to do is we're going to notice this symbol in the middle. And the symbol that is there in the middle is an equals sign. And it's always worth bearing in mind, remembering what equals actually means. And this symbol, there is a misconception that equals means and then the answer is. And it doesn't. Equals means, if two things are equal, they are exactly the same. Which is why we can have things like 1 plus 2 equals 3, because 1 add 2 and 3 are exactly the same things. Which means that what this question is saying to us, there is a number that when we times it by 2 and add 3, and when we times it by 4 and take away 5, we get exactly the same answer. Now, we don't know what that answer is. We just know that it's the same in both cases. The expression here on the left, there is a particular number, x, that when we do this to it, and when we do this to it, we get the same answers. And the next thing we're going to think about, for some inspiration on what to do with these, is we're going to think about one of these. Yes, a set of old-fashioned kitchen scales. And why on earth would we want to think about a set of old-fashioned kitchen scales? Well, the idea is, on one side of the scales, you put your weights. And on the other side of the scales, you put your ingredient. When the two are level, then you have got the same amount of ingredients as you have weight. So you put your weights on according to how much of the ingredient you want to weigh out, and when those two scales, when those two sides are balanced, are exactly the same level, then you have got the same amount of ingredients as you have weights. Now, there are three ways that we can keep those scales balanced. The first way to keep them balanced is to just leave them alone. Once they're balanced, once we've got the same amount of stuff on each side, then we just leave them alone and they will stay balanced. The other way that we can keep them balanced is if we were to add something onto both sides, but put the same amount of stuff on both sides. If we added, say, a kilogram to one side, we could add a kilogram to the other side, and they would stay balanced. And the third way that we can keep them balanced is if we were to take the same amount of information off both sides. If we were to take a kilogram away from one side and a kilogram away from the other side, say, they would stay balanced. The final thing that we need to remember when we're thinking about these kitchen scales is that it does not matter how many things are on both sides. For example, there is a set of kitchen scales. And let's say on one side we've got a weight that is 1 kilogram. And let's say on the other side we have got two weights and each one is 500 grams each. Are the scales balanced? Well, yes, they are. They are balanced because on this side we have got 1 kilogram and on this side we have got 500 grams and 500 grams. That's 1,000 grams. That's 1 kilogram. It does not matter how many things are on each side. There's one thing on this side and there are two things on this side, but that doesn't matter because the number of things on each side does not matter. What matters is how much is there. So these two scales are balanced. But why on earth are we talking about scales, and what on earth does this have to do with the question that we're looking at, the solve the 2x plus 3 equals the 4x minus 5? Well, these two scales are currently balanced. That means the weight on the left-hand side of the scales and the weight on the right-hand scales are the same. They are, in fact, equal, if you like. So what we are going to do is we are going to use all of that information about the scales to draw a picture that will help us work out the answer to this question. Best thing we can do is to actually just have a look at the drawing of the picture, and we'll work out where this is going as we do it. So our question is solve 2x plus 3 equals 4x minus 5. Now the idea is that these two equations are equal to each other. So what I'm going to do is I'm going to draw a set of scales. And on one side of the scales I am going to visually represent the 2x plus 3. And on the other side of the scales I am going to visually represent the 4x minus 5. How am I going to do that? Well, first thing I'm going to set up my blank scales, like this. Nice quick sketch of some scales. And on this side, I'm going to have two blocks that have got x's on them. That's the two x's. And I'm going to have a block for plus 3. I'm going to keep that as a plus 3. I need to make sure that I've got the plus symbol in there, just because we don't want to lose track of any information. On the other side, I've got 4 x's, so I'm going to have 4 blocks of x. That's 1, 2, 3, and then 4. And I'm going to have a block with the minus 5 in it. So there we've got 2 x's plus 3 and 4 x's minus 5. That's the two sides of the equation here. And they are currently balanced. They are equal to each other. Notice that it does not matter how many things are on both sides. There are more things on the right hand side than the left hand side, but they are still balanced. Because it doesn't matter how many things are there, it matters what is there and how much is there. They are balanced because they are equal. Now, there are 3 ways that we can keep these scales balanced. The first would be to leave them alone and do nothing with them. Well, fine, but then we wouldn't be any further on in the question. We could then keep them balanced, and this is where it gets more interesting. We could keep them balanced by adding some more stuff on to both sides. As long as we put the same amount of weight on both sides, we'd be keeping them the same. Or we can keep them balanced by taking the same amount of information off both sides. The whole reason that this question was so difficult is that we had x's on both sides. So trying to get rid of the x's on one side of this equation, either on the left or on the right, it doesn't really matter. Trying to get rid of them, but still keeping the whole thing balanced, would be a really good idea, because then we'd be turning it into something that's more like what we'd like to see. Something that's only got x's on one side of the equal sign, so that we could then solve it with a function machine. So we ask ourselves one very simple question. Is there stuff on both sides that we could get rid of? And when we say stuff, we mean x's. Is there stuff on both sides that we could get rid of? And if the answer to that question is yes, then we should get rid of that stuff. So, is there stuff on both sides of the scales that we could get rid of? And the answer is yes. Because we could, for example, get rid of this x block. We could take that away, throw it away, not interested in it anymore. And as long as we get rid of the same thing on the other side, an x over there, then the two sides of the scales remain balanced. We've taken an x weight off the left and an x weight off the right, and they are still balanced. But we could go one step further than that. We could take another one off there and another one off there, and they are still balanced. Is there anything else that we can get rid of? Actually, probably not. There's a 3 over here and a minus 5 over here. Well, let's not go mucking about with the numbers too much, because we'd have to draw them all out and that feels a bit overcomplicated. We're okay with the numbers being on both sides. That's not really a problem. And over here then we've got an x and an x, but there's no matching x's over here. So we've got rid of everything that's the same. Why is that useful? Well, let's just write down what we've got on both sides now. So on this left-hand side, we've got the plus 3. We've just got a plus 3 there. And on this side over here, we have got 2 x's and we've got a minus 5. We are left with 2x minus 5 over here and plus 3 over here. And these two things are what? They are equal to each other. They are equal. And does that look a little bit more like something that we could solve with a function machine? I would say yes, it does. Here is a piece of algebra equal to a particular number. We could tidy this up a little bit just to make it even clearer in two ways. The first thing we could do, we don't really need that plus sign on there. We could just turn that into a 3. In fact, it's not a -3, it is a +3, but we could drop the plus sign because we would never really bother writing it there. The other thing we could do is we could switch over the left and right sides of this just to make it look a bit more like we'd expect. We could take the 2x minus 5 and write that on the left hand side and the 3 and write that on the right hand side. That's okay, we've not changed anything, we've just swapped the order over to make it look a bit more like we're used to. And this is something we could solve with a function machine, and that is the whole point. And once we have got down to this bit, we can effectively rule off this stuff with the scales and we can just solve a function machine, because the question was solve 2x plus 3 equals 4x minus 5, and the question is now solve 2x minus 5 equals 3, and we could solve that with a function machine. So we're going to set up a function machine, and our function machine is going to look like this. The x goes in, first thing we do, we times it by 2, and then we take off the 5, and that spits out 3 from the other side. We're going to reverse that function machine. 3 goes back in, we add 5, and then we divide by 2. Reversing that machine, 3 plus 5 is 8, divided by 2 is 4, and we are suggesting then that x equals 4 is our answer, because we just turned it into something that we could solve with a function machine. Now we should probably check that. So what we might do is we might go off to the side and we're going to check it, and I would strongly suggest we do this. The way this question is set up, this says there is a number x that when we times it by 2 and add 3, and when we times it by 4 and take away 5, we get the same answer. So surely we could just check that. We could check if that is true for the number 4. So let's do the left hand side first then. On the left, 2 times 4 plus the 3, 2 times 4 is 8 plus 3 is 11. And on the right, we would get 4 times 4 is 16, and then take away the 5, 16 take 5 is 11. We get the same thing on both sides, and we do indeed have an answer in x equals 4. So what we did is we looked at this question, we said we can use this balancing scales idea of taking stuff off that's the same on both sides to tweak the question until it gets to a point where we can then solve it with a function machine. Once we're at that function machine bit, we can ignore everything we've done before, just focus on the function machine, and then we probably want to check our answer at the end. Let's have a look at another example and show that this will work every time. Solve 5x minus 23 equals 3x minus 5. So we've got this equation where we've got some x's on the left and some x's on the right. And as soon as we've got this kind of setup, we automatically should think, we can't solve this with a function machine yet. We need to use the scales to fiddle about with it until we can get it into a function machine problem. So we're going to set up the scales. We're going to set up our blank scales, and then we're going to sketch out what we've got left and right. Here we go then. So there's our blank scales ready to be set equal to each other. On the left hand side then we've got 5 x's, and we have got a minus 23. We are going to write that as a minus 23 because we don't want to lose any of the information in there. So there's 1, 2, 3, 4, 5 x's and a minus 23. And on the other side we have got 3 x's for the 3x, and we have got a minus 5. And they are equal to each other. How do I know? Because the question tells me that. So it doesn't matter that there are more blocks on the left than there are on the right. It does not matter how many things are there. It matters what is there. We ask ourselves one very simple question, and that question is there stuff on both sides that we can get rid of? Because remember, there are 3 ways we can keep these balanced. We can either do nothing, which seems a bit pointless, we can get rid of the same amount of information on both sides, or we can add the same amount of information onto both sides. And getting rid of stuff seems like the best way to go with this. So, is there stuff on both sides that we can get rid of? Yes, there is. There are x's on the left and on the right that we can get rid of. So we could, for example, get rid of an x and take those off. And we've reduced the amount of information on both sides. We could do that again though. We could get rid of this one and this one. There is a pair of x's, one on the left, one on the right, that we can get rid of. And we could do it once more as well. We could get rid of this one and this one. One from the left and one from the right. Is that it? Yes, it turns out that that is it, because while there are some x's left over here, there are no more x's left over here. We're not going to bother about the numbers too much because it doesn't really matter that there are numbers there. That will fix itself in the next step. Once we've got rid of as many x's as we can from both sides, then we simply look at what we're left with. So on the left hand side we are left with 2 x's and a minus 23, so 2x minus 23. And on the other side we are simply left with the minus 5. And that's okay, it's a negative number this time, but that's not a problem. These two things left and right are what? They are equal to each other, because the whole point is that the scales are still balanced, so they are still equal. This here is something we can now solve with a function machine. So we can effectively rule off, and we don't need to look at the scales anymore. We've dealt with them, we're not interested in them anymore. All we are interested in is this step here. 2x minus 23 equals minus 5, or more specifically, the question solve 2x minus 23 equals minus 5. So we set up a function machine. X goes in. The very first thing we do to the x is we times it by 2 to make it into a 2x. Then we have to take off the 23, and that spits out an answer of minus 5. If we're going to reverse that function machine, the minus 5 goes back in. The minus 23 becomes an add 23. And the times by 2 becomes a divide by 2. Minus 5 add the 23 will come out at 18, and 18 divided by 2 gives us 9. So we are suggesting then that the input x and the input 9 must be the same, and that x equals 9. We should probably check that, so off to the side I'm going to box off a little section here to do a check in. And the check I'm going to do is I'm going to test 9 in the left hand side, the 5x minus 23, and I'm going to test 9 in the right hand side, the 3x minus 5. And if I get the same answer for both of those sides of the equation, then it must be correct, because the whole point of this original equation, we are saying that there is a number that when we times it by 5 and take away 23, and when we times it by 3 and take away 5, we get exactly the same answers. So let's go for the left first of all. That's 5 lots of 9. Take away 23. Well, 5 9s are 45. Take away the 23 is 22. And on the right, we're saying that's 3 lots of 9. Take away 5. Well, 3 9s are 27. Take away the 5, 22. Look at that. It works. And the answer overall, x equals 9. Solve 2x plus 2 equals 14 minus x. So once again we've got this setup where we're going to have to draw some scales. So we can muck about with this question until we've got it into something that we can use a function machine for. So we're going to set up our scales. First of all, blank scales as always, with the nice balance in between. On one side then we've got 2x's and a plus 2. And on the other side we have got a 14 and we have got a minus x. And it is important that I put the minus sign on that x because it is a minus x. So we ask ourselves one very simple question. Is there stuff on both sides of the scales that's the same that we can get rid of? And the answer is, oh. Well, the answer is no. These two things are balanced, but here we've got x, and plus 2. Here we've got the 14. We're going to ignore the numbers, so we'll just focus on the x's. That's the x and the x. And here we've got a minus x. And an x and a minus x are not the same thing. And that presents us with the problem, because if we can't take stuff off both sides, then surely we can't do this question. Except we can. Because think about it, there are 3 ways we can keep this scale system balanced. The first is to do nothing at all. We leave it there and we move on. And okay, yeah, great. It's not going to get any harder than this, sure, but we wouldn't actually get anywhere with that. We wouldn't be solving the question in any way. The second way that we could keep this balanced is to take the same stuff off both sides. To take a certain weight off the left and a certain weight off the right, and keep them balanced that way. But we can't do that either, because we haven't got anything that's there on the left and the right that we can get rid of, like in the previous 2 examples. The third way we could keep these balanced is to add the same information onto both sides, to put a certain weight on the left and a certain weight on the right, a certain piece of information on the left and a certain piece of information on the right, to keep them balanced. But surely that's going to make it worse, isn't it? We're just going to end up adding extra stuff in and it's going to get difficult. unless we choose very carefully. And what I am going to do, just trust me for a moment and then I will explain why. I am going to choose carefully to put a block over here worth x. And I am going to choose to put over here a block worth x. Are the scales still balanced? Yes, they are. Because we have added the same information on to both sides. So they are still balanced. But why might I have chosen x? Because now we look carefully at what we've got over here on the right. And you may notice here that we have an x. And we have a minus x. And when we put x and minus x together, what does that leave us with? Why, it leaves us with 0. So I've chosen very carefully to put an x here on the left and an x here on the right, knowing that on this side of the scales and only on this side of the scales, the x and the minus x are going to collapse together into nothingness, and they are going to disappear. Now, it is very important at this point that I make clear that I am not crossing these out because they are the same anymore. This time I have chosen to add information onto both sides, and I am only crossing off on the right hand side because I chose carefully enough that the x and the minus x would cancel each other out, would collapse into nothingness. I am not going to cross anything out on the left hand side because there is nothing there that will collapse. I have chosen carefully that I'm going to add in an x on both sides, knowing that the x and the minus x will collapse into nothingness. So I've done the adding on first, and then I'm doing the crossing out. Don't get those two steps mixed up. And think really carefully about why we are crossing stuff off. Here we are crossing stuff off because the x and the minus x will cancel. And if you have any number of minus x's, if you have, say, minus 2x or minus 3x, minus 4x, you could add in x's on both sides to counter each of those minuses. Let's keep going with this question then and prove that it works. On this side then, x, 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 that's 3 x's and a plus 2. On this side, well, the x and the minus x have cancelled out, so we are just left with a 14. 3x plus 2 equals 14. That's something we could solve with the function machine, so let's set our function machine up. X goes in, times it by 3, and then we add 2. And out the end of that comes 14. 14 goes back in. Instead of the adding 2, we take away 2. And instead of the times 3, we divide by 3. So 14 take away 2 is 12. 12 divided by 3 is 4. And we reckon then the answer is x equals 4. Let's do a quick check. On this side then, 2 times 4. And then add 2. So on the left, 2 lots of 4 is 8. Plus the 2 is 10. And on the right, 14 minus a single solitary lot of 4 is 10. And look at that. It works. Let's do one more of these to make this point about the minus x and the cancelling out. Solve 4x plus 3 equals 45 minus 2x. So we need to set up our scales and sketch out what we've got then. On the left then we've got 4x's. 4, and we've got a plus 3. And on the right hand side we have got a 45, and we have got minus 2x, or rather a minus x and another minus x. That's 2 minus x's that we need to use there. That's the minus 2x. They are equal to each other. We ask ourselves one very simple question. Do we have stuff that's the same on both sides that we can get rid of? And the answer here, once again, is no. Because, ignoring the numbers, on the left-hand side we have got x's, and on the right-hand side we are dealing with minus x's. And x's and minus x's are not the same thing. That means that we have only got one option left to us, and that is to add stuff onto both sides. What am I going to add? Well, I'm going to add an x here above this minus x, and an x here above this minus x. Now, the only way I can keep that balanced is if I were to add x's over here. That's 1 and 2 on both sides. 2x is added to both sides. Why have I chosen to do that? Because now the next thing I can do is I can notice that here this x and the minus x will collapse into nothingness, and this x and this minus x will collapse into nothingness. Notice that I'm just crossing out on the right hand side because the stuff doesn't cancel into nothingness on the left. We had to add them on to both sides, but the fact that they then disappear is just because we picked cleverly enough. We've got rid of the x's on one side though. The x's over here have all gone. We're just left with a number on the right hand side, so we can just turn what we've got into an equation that we could solve. 1, 2, 3, 4, 5, 6 x's and a plus 3, so 6x plus 3, and on the right hand side simply 45. They are equal to each other. We can ignore the scales now and we are simply looking at this question here. Solve 6x plus 3 equals 45. That's something we can solve with a function machine. So the x goes in, we times that by 6, and then we have to add 3, and that spits out 45. Put the 45 back in. We're going to be taking away the 3, and then we're going to be dividing by 6. 45 take away 3 is 42, and 42 divided by 6, that spits out 7. So therefore our suggestion is that x equals 7. We should check that, so we're going to just box off over here for a check. And we're going to check the 7 in the left, check the 7 in the right, and see if we get the same answer in both cases. So on the left, we're going to do 4 lots of 7 plus 3. 4 7s are 28, plus the 3 is 31. And on the right-hand side, 45 minus 2 lots of the 7. 2 7s are 14. 45 take away 14, and that will be 31. Same on both sides, same left and right. Therefore, x is 7 is the solution to this particular equation.